So this equation is how it is written on your AP sheet. This is for forces in a wire in a magnetic field and what it's going to feel. So it's how it's on your sheet is ILB sine theta. Most typically, what do you think the angle is going to be?
90.
0 or 90, right? Most of the time it's going to be 90 because the sine of 90 is 1, okay? So that would be a situation where you have the wire going in one direction and the magnetic field going in like a 90-degree angle to it. Most of the time, the easiest way to remember this is what I always talk about. It's like, okay, force equals build. Now, it's just a rearrangement of it. But there's a couple of things that are important about the length of this wire. And this will play out large later on once we get moving objects going through magnetic fields. That L is just the length of the wire that is being exposed to the magnetic field. It is not necessarily the entire length of the wire. So one of the problems that we're going to do eventually, like we're going to have a magnetic field. Remember the lab that you all did where you had the really strong magnet? And you ran the
plates?
Yes.
And you pass them, yeah.
Oh. Yes. No. No. But now we're going to view it from the magnetic side of it, not the...
We're going to do the same lab.
Basically the same.
No.
A little different.
A little bit. Yeah,
The
same
math will
idea.
be different.
The math will be hard.
So
Plus the concepts.
So here's the story. So if this is a wire, and we'll get more into this tomorrow. So if this is a wire loop traveling through a magnetic field, if you're talking about the force part of this and the length, the only thing you would use is the length of the wire that's being exposed to the magnetic field. It isn't like the horizontal length, it's only the length that's going to be in the magnetic field. I'm just planting the seed right now. Just remember this, okay? I promise you, you're going to have a question like this on the test. I promise you. Only worry about the vertical distance that's going to be going into the magnetic field. This will make more sense later. I'm just telling you this so you can begin to remember it. Colin?
But isn't the magnetic field like a sphere? So why would you only worry about
No. This would be like you have a region in space that has a magnetic field.
Not as if you're not looking at the whole magnetic field, just
Yes, I'm just
The
looking
line
at that
goes
part that the wire loop is going into. Okay?
okay.
Just go with it. It'll make sense. I'm just telling you this because if I don't tell you this 4 or 5 times, you try to use the wrong length. So I'm trying to get this seed planted so you use the correct length when you get to this problem on the test.
Cool.
Okay? All right. Now, here's the problem when you have 2 wires. Okay? So when you have 2 wires, like we just talked about, this gets a little bit sketchy. Mainly because of the fact that if you look at the idea that how you calculate a magnetic field, so how do you calculate if you look on a magnetic field and you've got the magnetic field is mu naught I over 2 pi r, okay? So if you look at one wire with a certain amount of current, that's going to generate a magnetic field around it, okay? So that's going to be one magnetic field. So we're going to do a little bit of hocus pocus. So if you have 2 wires, and this will make sense in just a second, basically what we're going to do is a substitution into this equation of build, okay? But you've got to have 2 different lengths of wires. And basically, it's exceptionally rare that you don't use the same length of wire, like with the demonstration that I just did. And I've never seen it where you don't have the same length of wire, but it's just more of a, hey, let's make sure we use the same length kind of thing. So if you have 2 wires, what you end up with, and I'll explain all this in just a second. So basically, what I did is I took that F equals Bill, and you do this substitution in there for that magnetic field. Now, this equation is not on your equation sheet. If you need this equation for the test, I will give this to you. But it's a pretty simple derivation. So these are going to be your currents. Typically, your currents are going to be the same value. Now, obviously, if only one of the wires has a current, what's going to happen? Nothing.
Sorry, my shoulder is popping funny.
He had me feel it.
That's biology. You know the rules.
Stop it.
String them up.
I'd like to.
No.
So obviously, if only one wire has a current, guess what? There's not going to be a force, okay? And the L, you just assumed that the L was the same for both of them because there's no way to put in different lengths of wires, okay? So, but if you think about this, this makes sense. As the current gets bigger between the two wires, what's going to happen to the force? That's going to get bigger, okay? As the length of the wire exposed to the force gets longer, what's going to happen to the force? It's going to get bigger because you're going to have more of that value of that force in that magnetic field. This is either the radius or the distance between the wires, same idea, okay? Radius or distance. So as you decrease the distance, what's going to happen to the force? It's going to get bigger. Okay, there you go. All right, so today's assignment, there's going to be two parts to it.
Oh, no.
You're going to be fine, okay?
It's
Let me write the
killing
part
me.
out of the book, and then there's some things I really have to explain out of that, and then I'll hand out the next part of it. So Danny, stop that for a second while I